In 2018, I made an animation about the International Space Station. I showed all the pieces coming together, but I didn't show how it was done. These modules didn't just float together on their own, it was a lot of work. It involved mission controllers back on Earth, astronauts on board the station, and some fancy robotics. In this video, we're going to dive deep into the details to see how it worked. The International Space Station took over a decade to complete. Most of the pieces that you see here were launched by the space shuttle. In fact, this was one of the main purposes of the space shuttle. It was to build the space station. We can't go over every single mission. That would take too long for this video. What I'd like to do is talk about the initial stages of the station's construction back when the ISS was really small. We'll go over just a few of the space shuttle missions and how these pieces were put together. We've got to remember, the station isn't just aimlessly floating in space. It's going incredibly fast, about 20 times the speed of sound here on Earth. It orbits the Earth once every 90 minutes. Here's the front of the station. It always travels in this direction. So this is forward and aft, port and starboard, and then there's zenith pointing away from the Earth and nadir pointing towards the Earth. These terms are part of the regular vocabulary of an astronaut. We'll be using them a little bit throughout this video. This is what the completed station looks like. The only part that the astronauts can live in are the pressurized modules. When I say module, I'm referring to one of these cylindrical pieces of the space station. It has air to breathe, comfortable living conditions, and protects the astronauts from the vacuum of space. Each module has one or more berthing ports that can be connected to other parts of the station. Sometimes these are referred to as docking ports, but if we're being specific, it is a berthing port because the joining module or spacecraft must be assisted by use of a robotic arm. There are two main sections to the station. The Russian orbital segment, these are modules from Russia, and the United States orbital segment. These are modules from the United States, Europe, and Japan. You can see how the modules on each side look just a little bit different. On the US side, the modules are connected by the Common Berthing Mechanism, or CBM for short. There are two different sides to this, the active side and the passive side. Once these are brought together, latches pull them in close, and then there are 16 bolts to firmly mate them together. The space in between is called the vestibule. This will be pressurized with air. This process takes a few hours. Then the hatch is opened, some of the hardware is removed, and connections are made in between the modules, which includes oxygen, power, data, and water. Once finalized, there is a white protective barrier put in place. The astronauts can now move freely in between the modules. The Common Berthing Mechanism is used for modules that are permanently attached together, like the Harmony and Destiny modules. They can also be used for visiting spacecraft such as the SpaceX Cargo Dragon. The Russian side of the station uses a different docking mechanism that is not compatible with CBM. We need some way to connect to the different mechanisms. This is kind of like taking a power plug from the United States and bringing it over to Europe. It's not compatible with the wall plug. What do we need? An adapter. It's the same concept on the space station, but on a larger scale. Two different mechanisms, so we need an adapter in between. This is called the Pressurized Mating Adapter, or PMA for short. The larger side uses CBM, which can be attached to the US side of the station. The smaller side uses APAS. This is compatible with the Russian side of the station and with the space shuttle. On the station today, there are 3 of these adapters. PMA-1 is permanently in place, connecting the two sides of the station. PMA-2 and PMA-3 were used as docking ports for the space shuttle. The smaller side, which is the side that uses APAS, was used for the space shuttle. This is how it would dock to the space station. Both of these PMAs now have yet another type of adapter placed at the end. This allows for more modern spacecraft to dock to the space station. If you'd like to see this in action, you can watch my SpaceX Crew Dragon video. I'll leave a link in the description below. Now let's take a quick look at the space shuttle. The crew spends most of their time up here in the crew compartment. Back here is the payload bay. This is where the space station modules were carried up into space. Up front here is the orbital docking system. This is the place that could dock to the International Space Station. The astronauts can also do spacewalks from out of this hatch. On the side here is the Canadarm. It's a robotic arm that is capable of moving things around in space. The arm can be controlled from inside of the space shuttle at this workstation. The space shuttle launches took place from Kennedy Space Center in Florida. Once in space, the payload bay doors were opened. They remained open for the entire time they were in space. Then it took a few days for the space shuttle to catch up with the ISS. The space shuttle is retired now, but it played a crucial role in building the space station. Let's take a look at a few of these space shuttle missions. This first mission we'll go over in a bit more detail. I want to give an idea for the timeline and how long things took. And then for the next 3 missions, we'll go over just a little bit quicker once we get the right idea. The first mission we'll talk about is STS-88 in December of 1998. And the STS stands for Space Transportation System. All shuttle missions started with these 3 letters. This was the first shuttle mission to the International Space Station. At this time, the station had only one piece. It was the Russian module Zarya orbiting the Earth all by itself. On the completed station, this is where Zarya is. And this first shuttle mission brought up the Unity module. This is kind of like the center hub of the station, with 6 berthing ports where other modules can be attached. Unity was launched with PMA-1 and PMA-2 already attached to it. This mission took almost 12 days to complete. The first few days were used to make preparations and to catch up to Zarya. On day 3 of the mission, the Canadarm was put to work. It was time to lift Unity out of the payload bay. PMA-2 was then attached to the orbital docking system on the shuttle. The Canadarm can move large masses in space due to being weightless while in orbit. It had to move very slowly to not strain the robotic joints. It took hours to complete and very careful movement. The shuttle's thrusters were fired to bring the modules together. On the 4th day of the mission, the space shuttle slowly approached Zarya. The Canadarm grabbed onto it and then moved it into position above PMA-1. Again, the shuttle's thrusters were fired to bring the modules together. It took a few more days of preparation before they could go inside the station. There were 2 EVAs where they get into their spacesuit and go outside the station. They connected cables and installed antennas on the outside of the station. The Canadarm was used to help move the astronauts around. On the 8th day of the mission, they opened the hatch and entered the station for the first time. They only stayed inside for about a day, just enough to check things out and prepare it for the next mission. On the 10th day of the mission, there was one more EVA to finish the installation. Then on the 11th day of the mission, the shuttle undocked from the ISS. At this point, there was no permanent crew yet. The station was too small. Unity and Zarya orbited all by themselves for the next few months. Of course, all while being monitored by Mission Control back on Earth. Then we'll fast forward just a few years in time. The station had a few more modules, and there were 3 crew members living on board the station. The next mission we'll talk about is STS-98 in February of 2001. So here's our completed station. Here's what it looked like right before STS-98. This mission brought up the Destiny module. STS-98 lasted for 13 days, but they were attached to the station for only 6 of those days. They docked to PMA-3 on the nadir or bottom side of the station. The Canadarm was used to grab onto PMA-2 and relocate it to the side of the Z1 truss. Then the arm was used to lift the Destiny module out of the payload bay, slowly flip it 180 degrees, and then attach it to the forward berthing port on Unity. This took hours to complete and very careful movement to make sure nothing was damaged. The next day, they opened the hatches and went inside Destiny for the first time. The US laboratory is mainly used for scientific research on board the station. PMA-2 was then relocated to the forward side of Destiny. The mission had 3 separate EVAs to connect and install items on the outside of the station. The purpose of this next mission was to give the station its own robotic arm, called the Canadarm2. The first Canadarm was on the space shuttle. Very useful, but it was permanently attached to the shuttle. This means it goes home at the end of a shuttle mission. The Canadarm2 can lift heavier loads and would now stay on board the station, so it can be used in between shuttle missions. Here's an example of where you might find the Canadarm2 on the station today. The arm can attach to the station at either end. These are called latching end effectors. It attaches to anywhere on the station that has a power data grapple fixture. As you might guess, it provides power and data connection so it can be controlled from inside the station and from mission control back on Earth if needed. These power data grapple fixtures are in many places on the outside of the station. The mission that brought up the Canadarm2 was called STS-100. It was a 12-day mission. The shuttle docked to the front of the station at PMA-2. This carried Raffaello, a multi-purpose logistics module which would be temporarily attached to the station. The second piece of cargo was the Canadarm2. It was brought to the station on board a special pallet. The shuttle's Canadarm grabbed onto the pallet and lifted it out of the payload bay, and then attached the pallet to the top of the Destiny module. It was slowly unfolded and put together by the astronauts. They also had a little help from the shuttle's Canadarm. Then the Canadarm2 was moved on its own for the first time. It was initially connected to the side of the Destiny module. At the end of the mission, the Canadarm2 was used to lift the pallet and hand it over to the shuttle's Canadarm. This was the first robotic handshake in space, sometimes referred to as the Canadian handshake, because both of these arms were built by Canada. The empty pallet was then put back into the payload bay. A few days later, the shuttle undocked from the station. The Canadarm2 was essential for constructing the rest of the space station. The last mission that I want to show in this video is STS-104. So here's the completed station, and here's what it looked like right before STS-104. This mission brought up the Quest airlock. The mission lasted for almost 13 days, once again docking to the front of the station at PMA-2. This was the first time they used the Canadarm2 to help construct the station. The Quest airlock was slowly moved into position on the starboard side of the Unity module. 2 of the astronauts were in position, ready to help install the new module. Once Quest was installed, it was time for the high-pressure gas tanks. Once again, the Canadarm2 was used to move the tanks around. The astronauts helped guide the tanks into position. Up until this point, they could only perform spacewalks from the shuttle's payload bay. But the Quest airlock gave them another option. This part is called the equipment lock, and this part is called the crew lock. Once the astronauts are inside of their spacesuits, the hatch is closed and the crew lock is depressurized. This means that all the air is pumped out. Now the airlock hatch is opened, and then the thermal cover on the outside. The opening points straight down, so the first thing they see is the Earth right beneath them. This video summarized 4 separate shuttle missions, just to give you a better idea of what it took to construct the International Space Station. This was just the early stages, and there's a lot more to the construction. Maybe we'll cover that
my name
in
is
a
Dr.
future
Mark
video.
Fernandez, and I'm the principal investigator on the Hewlett-Packard Enterprise Spaceborne Computer 2 project. Spaceborne Computer 2 consists of 2 twin lockers, each containing 2 HPE computers designed to conduct scientific experiments aboard the International Space Station as it orbits the Earth. In one of the Spaceborne computer systems, we use a mix of 12 gig value SAS and 24 gig enterprise SAS SSDs. These offer proven performance and reliability. We like reliability on the ISS. Also, this is the first time over 130 terabytes of data storage has been sent to the ISS. This SAS-based storage is used to capture and process raw data from scientific experiments and produce results that are then transmitted back to Earth. SAS technology is one of the storage technologies used in cutting-edge experiments aboard the ISS today. Spaceborne Computer 2 is the latest available edge computing resources on the International Space Station. We had to survive the shake, rattle, and roll of launch. We had to properly package it so that it could be stored properly, and we had to come up with the instruction set on how it would be installed by our astronauts. The latency from space on the International Space Station is significant. It takes a very long time to get the data from the International Space Station back to Earth.
The space station has limited bandwidth. We are only allowed to use 2 megabytes per second for only 2 hours per week. So that means if you're running experiments that uses a lot of data, you can't send all your data down to Earth. You need to do some processing using the power of HPE's Spaceborne Computer 2, take a look at your data and distill it down to what's interesting. Then you can send down interesting events down to Earth where you can then leverage the power of Azure and the public cloud to process at scale. With that, we can also bring tools to bear such as Microsoft Genomics. And we take that sequencing data and see, is there anything interesting that we need to tell the astronauts about what we have seen?
One of the great things about Spaceborne Computer 2 being developed with an open source software is that here on Earth, it's really cool that for me as a developer, I can use those same tools. It really increases the developer velocity to creating something useful. So I can know with confidence that, say I go to the repository for this project, I can clone it from GitHub, I can open it in a browser with GitHub code spaces, or I can open the solution with Visual Studio Code, build it with Docker, and I have the exact same tools that I know are going to be present in the Spaceborne Computer 2. So I can validate, dev, and test locally, deploy to Azure, and deploy to space confidently. It's cool that we can take patterns that we know exist today, repeat them, stand on the shoulders of the giants that came before us, and build better things.
With stuff that every developer knows how to work with, building on open source components of Linux and Docker containers means that there's a much wider group of developers that can develop applications that are meaningful in space.
Open source technologies allow us to create unique and interesting things, and then Spaceborne Computer 2 gives us the horsepower to do them.
By conducting experiments with off-the-shelf technologies on the HPE Spaceborne Computer 2, we can prepare for missions that are further out. So if we're preparing to put humans on the moon or on Mars, we want to know how we can build these patterns of processing at the edge and bursting down to the cloud now while we have the space station before we go to much further and more difficult places. I'm looking forward to seeing how Microsoft brings our experience with democratizing the technology to help bring space out to every industry.
When we build these things today, our hope is that we can build truly game-changing things in the future for both astronauts on board, our partners, and the people here back on Earth.
So podcast number 77 was about this guy. This is the Spaceborne Computer 2 chassis. This is what's on the ISS and is acting as their supercomputer. It's pretty dang tight in here. And when it's fully outfitted, it would have HP Edgeline and HP DL360 servers inside. Here's a little flyer that would describe what's in there. Like I said, podcast 77, we've got a detailed conversation on this guy. They're working on Gen 3 right now, Spaceborne Computer 3 with HPE and Kioxia. And if you happen to be at the show, they're giving away a space station Lego, so check it out.
In a world where astronauts live and work in space, where tasks aboard the International Space Station can be time-consuming and dangerous, who will we turn to? NASA, in cooperation with General Motors, presents a Johnson Space Center production, the first robotic crew member in space, Robonaut 2. It travels to the space station this fall to give NASA a deeper understanding of human-robotic cooperation. Help is on the way. R2.
Meet Robonaut 2, R2 for short. R2 leads an amazing life on board the International Space Station as the first humanoid robot to travel in space. R2 is one of the most sophisticated robots ever designed, and was designed to assist astronauts on tasks either too dangerous or too mundane, and now NASA is looking for your help to make it more capable than ever before. NASA is launching algorithm-based coding competitions whose outputs will help Robonaut gain tremendous dexterity and the ability to operate an LED task board. Imagine your code and your solutions helping to control R2, assisting NASA and their astronauts in the pursuit of accomplishing more unique and exciting science on orbit. Do you think your code and your solutions can help advance humankind by advancing a humanoid kind? For more details on the Robonaut contest, visit topcoder.com/ISS.
Robots in space. We're familiar with seeing this in sci-fi movies, but did you know that in 2011, NASA made that possible when their robot called Robonaut, or R2, became the first humanoid robot in space? R2 lived on the International Space Station, where it launched to from the Space Shuttle Discovery on the STS-133 mission in February that year. R2 was developed by both NASA and General Motors to work alongside astronauts and perform simple tasks. The robot was designed to look and work like a human, with human-like hands and arms, and the ability to use the same tools as the crew. It was initially deployed as a torso-only humanoid, but in 2014, it was upgraded with 2 legs to allow it to maneuver inside the International Space Station. Although its primary job for now is demonstrating to engineers how dexterous robots behave in space, the hope for NASA is that, through further upgrades and advancements, it could one day venture outside the station to help spacewalkers make repairs or additions to the station or perform scientific work. Robonaut was also paired with a 4-wheeled base and tested during the 2011 Desert Rats, or Research and Technology Studies mission in the Arizona desert. R2's original tasks include hand drill cleaning and velocity air measurements, both being simple but necessary tasks that require significant crew time. It was a prototype meant to be used here on Earth as a way to better understand what would be needed to eventually send a robot into space. However, when it was unveiled, the system was so impressive that mission managers decided to go ahead and send it to the space station after a few upgrades. Outer skin materials were exchanged to meet the station's flammability requirements, shielding was added to reduce electromagnetic interference, and processors were upgraded to increase the robot's radiation tolerance. Operators have several options for how to control the R2, including both station crew members and controllers on the ground. One improvement over the previous Robonaut is that the R2 doesn't need constant supervision and was designed to be set to tasks and then carry them through autonomously with periodic status checks. Although NASA initially had no plans of returning R2 to Earth, as of October 2024, the robot is on loan to the Smithsonian for display at the National Air and Space Museum's Stephen U. Varghese Center in Northern Virginia for at least the next 4 years. So if you're nearby, you can actually see it in person. though unfortunately it is not operational and does not move while on display. The exhibit includes a video of R2 doing various jobs in space and its position to point at the Discovery, the vehicle that carried it into space. How do you feel about humanoid robots working in space? I don't know about you, but that's a job I don't want. Let me know in the comments section below, and to stay up to date with future content, hit that like and subscribe button. Thank you all for watching, and until next time, save that money. Robots in space. We're familiar with seeing this in sci-fi movies, but did you know that in 2011, NASA made that possible when their robot called Robonaut, or R2, became the first humanoid robot in space. R2 lived on the International Space Station, where it launched to from the Space Shuttle Discovery on the STS-133 mission in February that year. R2 was developed by both NASA and General Motors to work alongside astronauts and perform simple tasks. The robot was designed to look and work like a human, with human-like hands and arms, and the ability to use the same tools as the crew. It was initially deployed as a torso-only humanoid, but in 2014, it was upgraded with 2 legs to allow it to maneuver inside the International Space Station. Although its primary job for now is demonstrating to engineers how dexterous robots behave in space, the hope for NASA is that, through further upgrades and advancements, it could one day venture outside the station to help spacewalkers make repairs or additions to the station or perform scientific work. Robonaut was also paired with a 4-wheeled base and tested during the 2011 Desert Rats, or Research and Technology Studies mission in the Arizona desert. R2's original tasks include hand drill cleaning and velocity air measurements, both being simple but necessary tasks that require significant crew time. It was a prototype meant to be used here on Earth as a way to better understand what would be needed to eventually send a robot into space. However, when it was unveiled, the system was so impressive that mission managers decided to go ahead and send it to the space station after a few upgrades. Outer skin materials were exchanged to meet the station's flammability requirements, shielding was added to reduce electromagnetic interference, and processors were upgraded to increase the robot's radiation tolerance. Operators have several options for how to control the R2, including both station crew members and controllers on the ground. One improvement over the previous Robonaut is that the R2 doesn't need constant supervision and was designed to be set to tasks and then carry them through autonomously with periodic status checks. Although NASA initially had no plans of returning R2 to Earth, as of October 2024, the robot is on loan to the Smithsonian for display at the National Air and Space Museum's Stephen U. Varghese Center in Northern Virginia for at least the next 4 years. So if you're nearby, you can actually see it in person, though unfortunately it is not operational and does not move while on display. The exhibit includes a video of R2 doing various jobs in space and its position to point at the Discovery, the vehicle that carried it into space. How do you feel about humanoid robots working in space? I don't know about you, but that's a job I don't want. Let me know in the comments section below, and to stay up to date with future content, hit that like and subscribe button. Thank you all for watching, and until next time, save that money.
NASA Astro B robots will launch in space this month. The free-flying robots will operate inside the International Space Station (ISS) alongside astronauts.
The International Space Station is both a research lab and a stepping stone for future trips to the Moon and Mars.
The Astro Bs will replace the spheres, the current robots, and most used ISS payloads.
Fully autonomous, each 1-foot cube is packed with sensors that open up new areas of research. The Astrobees provide a zero-G research facility for guest scientists, give ground controllers additional eyes on the spacecraft, monitor radiation and air quality that help keep astronauts safe. Like a quadcopter, Astrobees fly in air, except there is no gravity on the ISS. As a result, they are not limited by lifting power. Larger payloads can attach in a tractor-trailer configuration, and multiple Astrobees can even work together.